All right, so the last question that we have to finish up with here on this whole chapter, right, is this one here. So let's clean it up from, there we go. There we go. Nice, clean working area. I'll even get rid of that. There we go. Yeah, let's get rid of more of that. All right. And that. And that. That's okay. All right. All right. Looks good. Yeah. All right. Kind of like a little Bob Ross show going on right here. All right, so we draw a little happy line down the middle. There's no wrong way to do that. No, no, we don't do that. And put little strokes through there like that and make it look like it's striped. I like to say striped instead of striped. Makes me sound fancy, Shakespearean. All right, yeah. Why do we not draw a line down the middle there? Because we are solving. Okay, in 0 to 2 pi. So again, this is coming from your middle section. You do have two variable terms. You could get everything on one side and set it equal to 0. But as you take inventory, you notice that your angles are different. And your primary concern is to get them the same. They don't always have to be single x's, because we learned yesterday that we could solve it with a multiple angle, but they do have to be the same. So let's go for it. What do y'all tell me what to do? You want to bring them across and set it equal to 0 first? We said that yesterday would not be a bad thing. So, okay. Because there's more than one variable term. And now it's equal to 0. Okay, so now we can focus on getting them the same. We can either build a 2x up to become a 4x. And remember, we do have an identity that builds angles up, right? It's the power reducing identity. So if I want to reduce the power by a factor of 2, it's signed to the first now. I would have to turn that into a square root of sine just to double the angle to get a 4x, right? No, thank you. No, that's not the wisest choice. But I can tear down a 4x pretty easily into a 2x, either by using composite identities or, in this particular case, because 4x is twice 2x, I can actually write sine of 4x as sine of 2 times 2x. Yes? Okay. Or you can write it as 2x plus 2x and do the composite identity. So here we go. Let's use the double angle identity. So let's come up here real quickly. Sine of 2x, remember, is 2 sine x, 1x. 2 sine x cosine x, sorry. It doesn't really matter what x is over here as long as it's twice over there. So, this could be a 5x on the right and a 10x on the left. Okay, so in this case, we have it as 2x. So sine of 2 blob is going to be 2 sine of blob cosine blob. Are you okay with that? As long as you can write it as 2 times something, then that something goes over there. And I was able to write 4x as 2 times 2x. Again, if that feels uncomfortable, just write 4x as 2x plus 2x and use the composite identity. But you will have to be careful because it's subtraction and you would have to distribute the negative. Okay, so now that we have the angles the same, we don't have to get them in 1x's, they're the same. It's already equal to 0, so what's our next task or agenda, goal? Now that it's already equal to 0. Factor it. Good. And the first rule of factoring is to look for a common factor. Well, we now have a common factor of sine of 2x. So when we factor it out, we're left with a 1 where it used to be minus the 2 cosine of 2x equaling 0. And now we set each of those equal to 0. Sine of 2x equals 0, or 1 minus 2 cosine of 2x equals 0. So let's go ahead and solve that second one. If I bring that across and solve, I get cosine of 2x equals 1/2. So now I have two trig functions to solve, which means it's everybody's favorite time, right? Unit circle time. All right, so remember with double angles or triple angles as we saw yesterday, you're going to have to realize that you're going to have twice as many solutions as you normally would have, right? That's what the 2 means. For every one that you would have normally around the unit circle, you're going to have 2 of them. Because remember, we're compressing the graph of sine by a factor of 2. There's 2 full cycles where we used to see just 1. So we did this yesterday. Pretend it's just sine of 1x. Where is sine equal to 0? At pi and at 0. So those are the 2 places. So I'm going to write them stacked. And remember, we say plus 2 pi n plus 2 pi n. Those are coterminal angles. That's the procedure. Whenever you have a multiple angle that you're solving, you want to say plus 2 pi n, because you're going to have to generate equations. All right. Now those are not equal to x. Those are both equal to 2x. So we have this system of equations now. And all we have to do is solve for x. So we'll multiply everything through by a half. Okay, so on the left, the half of 2 is 1, so we just get x. A half of 0 is still 0. And what's a half of 2 pi? 1 pi. Well, guess what the period of sine of 2x is? It's 2 pi over b. It's 2 pi over 2. It's pi. So that this generator right here, multiples of pi, that's multiples of the new period. Okay? And for the second one, we do the same thing. We multiply through by a half. And we get x equals half of pi is pi halves plus pi n. These now are your gen EQs, your generating equations. So let's go ahead and generate them, and then we'll jump to the other equation. If you start with the first one, all you have to do is just take the number that's showing for the first one. In other words, let n equal 0. And we get 0, right? Now that would be the only solution normally, but because we compressed it by a factor of 2, now I'm going to let n equal 1, and I get 0 plus pi, which is pi. So there's the 2 solutions from that formerly 1 solution. And yesterday we had 3. All right, now we'll do the next one. Pi halves is going to be the first one when n is 0. And now if you let n equal 1, you add pi to pi halves to get what? You ate a pie, you ate a half a pie, and then you ate a whole nother pie, you pig. How many pies did you eat? 3 pi halves, good, okay? And those are the other 2, okay? So the first equation generated 2, the second equation generated 2. That's the number that's in front of the angle. But we have another equation now on the right-hand side. So let's go for it. Same idea. Where does cosine equal positive a half? Yeah. Yeah. It's going to be quadrants 1 and quadrants 4. What's your reference angle? Pi 6 or pi thirds? Pi thirds. So the first one is pi thirds plus 2 pi n. And the second one is 5 pi thirds. Good. Quadrant 4, 5 pi thirds plus 2 pi n. Now those would be the only 2 solutions if that were cosine of x, but it's cosine of 2x. So each of those is going to generate how many? 2, right? So let's go ahead and multiply through by a half again. So we get x equals pi thirds times 1/2 is pi 6, which makes sense. It used to be a pi thirds. We've compressed it by a factor of 2, plus pi n. And then this generating equation is x equals half of 5 pi thirds, which is 5 pi 6 plus pi n. All right, then we get your gen EQs, generating equations. All right, so we're going to list them again very similarly. If you just start with the top one, the first one is going to be that first number. And again, when n is 0, we get pi 6. And now all we got to do to get the second one from that same equation is add pi to it. Well, what's a good version of pi here? 6 pi 6, right? So we get 7 pi 6. And notice, is 7 pi 6 still between 0 and 2 pi? Yeah, it is. What if you added another pi to it? What if you used that equation and added another pi? That'd be another 6 pi 6 to 7 pi 6. What's 7 plus 6? 13 pi 6. Is that bigger than 2 pi? Yeah. So again, that number will tell you how many each of those have. So there's the 2 from that one. And then we jump down to the bottom one. When n is 0, we get 5 pi 6. And now when n is 1, we just add pi to that, or 6 pi 6, and we get 11 pi 6, which we know is in quadrant 4. If you were to add another 6 to that, you get 17, and that's bigger than 2 pi. All right, so this equation would have had 4 solutions normally, right? 0 pi, pi thirds, and 5 pi thirds. But instead, because it was a 2x, Not 4 solutions, but it ended up having 8 solutions between 0 and 2 pi. And there they are. There they are. Let's take a look and see what that might look like graphically, since this was the last one that we did. You don't have to jump up and grab a calculator, but if you want to, you can. There it goes. Smart view. The only way to view. Do. Anybody know any good, clean, short jokes? Oops, too late. All right, so let's check our mode. We want to be in radian. I was in degree. Now here's what we're going to do. Typically, like if you go on next year and take calculus, which I hope many of y'all do, one of the 4 big things that we do on the calculator is solve equations. And especially when we have a variable equaling a variable equation, I would encourage you to, instead of graphing the left side in y1 and the right side in y2 and looking to see where they intersect, they might intersect in Timbuktu, right? Off your viewing screen. So what I would encourage you to do is get everything on one side and set it equal to 0. So now I'm going to graph this in y1 and I'm going to graph 0 in y2. I always know where 0 is, right? It's the x-axis, so that's why we do it that way. So let's type this in. We're going to get sine of 2x, and then I got to close the parentheses because your calculator always opens them, and I'm frozen, and okay. Sometimes it just needs a little extra attention, right? Don't we all? 2x minus sine of 4x, and notice I already have 0 graphed in y4, so that'll work. I'm going to go to my window now, and I'm going to go from 0 to 2 pi. So that's 2 pi. And because now I'm looking for the x-intercept, negative 10 to 10 is a good standard viewing. I'm going to leave it negative 3 to 3. Okay? I like to stretch out the y-axis and keep the x-axis in the middle. How many points of intersection or x-intercept should we see? 8. Okay? You want to count them? 1, 2, 3, 4, 5, 8. That was fast. Thank you. Does 0 count as 1? Here's 0, right? Does that count? Well, we're on the interval from 0 inclusive to 2 pi, so yes, 0 counts. But, Carl, does 2 pi count? No. Okay. So there's the first one at 0. 1 many, 2 many, 3 many, 4 many. And now look at all repeats. 5 many, 6 many, 7, 8. Yeah. Now, let's find this guy. Okay, that guy. Second trace, number 5. Intersect, right? And then it says, is this your first curve? You can just hit enter. Is this your second curve? Yeah, hit enter. And now let's scroll over to that one, closer to that one. We've done this before. Looks like it's close enough. So I'm going to hit enter. And I get 1.570. Isn't that great? Which one should that be on my paper? This should be the third largest, which would be yeah, that's kind of hard. Pi halves, maybe, right? That looks like pi halves. Yeah, if you come up here, you get out of there and you say x, it stores it as x, right? And if you type in pi halves, pi divided by 2, there it is. So, yeah, we found the exact values. It works. It works. Okay. Ain't that pretty? So notice it is cyclical, right? This thing has it goes down and then up and then down and up, and then it makes one little loop. And then it does it again, right? Down and up and down and up. So this is like a modulated sine and cosine. This is how real waves kind of go through the air. They're not perfectly sine and cosine waves. They get interference. If two waves like collide with each other, they end up combining together to form a new wave. Okay? Yeah. All right. Anything else? Any questions on this section? Like how much fun it was? Yeah, it was. I think that you all are knowing your identities now, so y'all should be in good shape. All right, so we'll conclude all the new lessons for the entire year.